We covered a lot of ground. Oh, Neil, there you are. I thought I had my vision skewed. We covered a lot of ground, and it went great. And the reason maybe it didn't go as great as I liked is it was an incredible amount of material, and it's just I don't expect you to absorb every bit of that. I mainly want to give you the main ideas. But so, in order to get this under this condition, in order to deduce this under the only condition is that tau is a stopping time, the first thing we had to do is define what a stopping time was. And in the new homework assignment, there's a problem just to help you practice what that means, because it comes up so often in the theory of Markov chains. It's really fundamental. But then we had to know what a super martingale was. So you had to, if you don't remember that was a chore as well. And then there's something called the dominated convergence theorem, because what we did is we bounded the stopping time tau so that these guys would be finite valued. Most importantly, this was finite valued, so I didn't have infinity minus infinity on the left-hand side. And so I had to bound an inequality like this, indexed by a capital N, and as n got larger, this increased. And there's something called the monotone convergence theorem that allows me to take that limit. So if you don't know what that is, you have no idea, you can't understand the proof either. Now, I also left something out. There's actually another term you can keep in here. I said, well, that's non-negative, so I can get rid of it to get a bound. It's often useful to include this in here. Why did I drop it? Because it needs Fatou's lemma. So we would have a reduced tau so that this thing would be meaningful, and then we let n go to infinity. Well, to justify that, you need Fatou's lemma. And so how many people here know what Fatou's lemma is? I didn't think so. So that's why a couple of so anyway, so you do need a bit of mathematics to get this all in. Hopefully I've given you just the main idea. And the main thing is martingales are such a joy in this area. They pop up everywhere, and so it's good to bring them up from time to time. We'll definitely need them when we get to stochastic approximation. And analysis of stochastic approximation is based on properties of martingales. We're not going to go and develop the whole theory of martingales, but I'll tell you some properties we'll use, and we'll go forward. All right. Okay, so I gave one application last time. Let me give another one. Okay, so there's this book I've mentioned with Richard Tweedy, who sadly passed away when he was younger than me. He was in his early 50s. That's from a heart attack. There's so many different kinds of Lyapunov conditions. We came up with a numerical scheme, and the third one is called V3. The V is because V is the Lyapunov function. And it looks a lot like this thing that appeared in the comparison theorem, except for the G is specialized to being a constant times the indicator function of a set. And if we're in a countable state space setting, we're going to take S to be finite. So in the book, we don't take S to be finite. We take it to be what's called small, which is a fundamental concept in this theory. Forget it. We won't do that. We'll just take the countable state space, assume S is finite, and basically, think about S. I mean, in a general state space, typically S would be compact, and so outside or bounded. So outside of a bounded set, you've got this negative drift. And it's big in the sense only that we assume F is bigger than 1. So last time I looked at the case where f was identically 1, and that was called Foster's criterion. So last time, at the end of lecture, I said, what the hell, let's do it. I took the case where S was a singleton, not a finite set, but one point. And I plugged in tau in that case. In that case, G is just 0, you know? Because where tau is the first heating time to that point, take it to be that. G is 0 up until you hit that point. And so you get a bound on the first return time to a point. But you can see you can do the same thing with a function. So before I took f equals 1 last lecture. But we can, you know, obviously, under this condition, we would have an inequality like this, where again, G is given by this. Let me explain that. I mean, it's right in front of us, but okay, so I take this thing, I've done two things. I'm replacing tau by the first return time to a point. So that's what I call tau sub x star. X star is this point that I assume I can reach from every initial condition. And so under that condition, x at tau star, well, tau star is a particular time at which we visit this point. So x of tau star is, I mean, x at this hitting time is just x star, right? You know, this is a, I mean, I'm saying I'm taking a time at which I visit this state. So at that time, I'm at that state. Okay, so this becomes deterministic. I get this, and then I get this again. If G is given by this B-indicated function S, then this whole thing is 0 except possibly the first term. T equals 0. All right, is that clear? Oh, wait. No, I'm sorry, that was the point. I'm sorry, I made a mistake. You guys don't agree with me when you know I'm wrong. If S were a singleton, that was last lecture. No. Everyone wake up. I went back into last lecture. I see one other mistake here. I forgot the -1. Okay, cool. All right. Now do you see any of the other typos? I think that's good. So all I've done is I've rewritten this down and then just used some interpretations. So I'm not going to do it. So I made you all notes, and you can see for yourself that under the unit chain condition, that is uniformly bounded. Or more precisely, X star irreducibility. And just try to get some intuition about this. It's sort of it's like a geometric trials argument. You know, that sum is 0. Suppose a chain just blasts off to infinity. Well, this is a finite set. I'll see it a couple of times and goodbye. So the sum is finite. Suppose then that doesn't happen. I visit S. Well, then there's a positive probability that in 10 seconds I'll see X star. Okay? And when I do, it's over. I stop. Okay? All right. Maybe I wasn't so lucky, but then I hit S again. I flip it independent past, and after 100 seconds or something, there's a positive probability I'll visit X star, and you can bound all this perfectly. I mean, it's not a long proof. It's just that we don't have time for it. It's quite a pretty proof, actually, and it's in the notes. There's 2 different ways to prove this is bounded, and one is to make precise this heuristic I just gave you. You know, and the other is an operator theoretic approach, which is pretty cool too. And you can forget the sample path sort of representation and write this in a different way. Okay, so this turns out to be, and what's really cool is this is even if this is infinity, you know, even if this is infinity with positive probability, this is always bounded. You can get uniform bounds, you know. So that's a really cool tool. So I did all this without assuming that thing is just still there, right? But then you say, I've proved this is finite regardless of whether tau X star is finite or not. And then, therefore, this must be finite. Because F is greater than or equal to 1, okay? And so the fact that F is greater than or equal to 1 means that not just that tau is finite valued, but its mean is finite, you know, has the first moment. Right, that's greater than or equal to 0. F's greater than or equal to 1. So this entire sum is greater than or equal to tau X star. All right. So if you just, again, faith-based mathematics, if you accept that this is uniformly bounded in X, then it follows that this is finite valued, and therefore that occurs with probability 1. Yep. All right. No? You don't like that? Oh, I see. Oh, that is a lot to walk in late on. Okay. Yeah. All right, but
so tau X star, that's
yeah.
I mean, what does this all this saying? Like we can reach one of these. You know, we can reach this 3 finite time.
Yeah. So let me go. I'll write down a theorem for you, and to summarize all the conclusions. You know, and so remember how did this come about? So why was this important? So remember, I'm using pi of f just to denote the mean, the steady state mean of a function f under a probability mass function pi. We saw that that's equal to something like that. I ran out of room there to write it down. That's the first return time to X star. So that's not quite how we wrote down Keck's theorem. I divided by the mean return time. This is the same as Keck's theorem as we described it. Okay. So right away we know that because this is now finite valued, we know that the mean of f is finite and we get a bound. All right? 2, the solution to Poisson's equation. It was just like this. So you know, we'd like this to be, we'd like to know what H is. We'd like to, yeah, I mean, we want all sorts of things. Later on we'll want to know its structure, because we want to be able to approximate it. But this tells us at least, you know, given this upper bound, we know that without the tilde, without the subtraction, we have an upper bound based on V. And pi of f is finite, we just said that, right? And we said that the mean of tau is finite as well. So we get a bound on H. H is bounded by a constant times V. I'll put in +1 there to be safe. I mean, we've got a constant times V, and we've got, there's a constant here that's something strange. But we get a growth rate for H, you know. And often we're going to want to get a growth rate because we're going to choose a basis for approximation, and we want to say, does it have? First of all, we'll probably in a lot of models will say, it's convex, and then we're going to want to know its growth rate. Is it quadratic, cubic, exponential, and we'll fit a basis based on that insight. So the first thing we'll do is we'll get a crude bound, and then we'll refine it. You know? Answer your question? That's the motivation. Yeah.
I didn't have a specific question, but
yeah.
Followed all that.
Yeah. Okay, anyway, so that's why this is fundamental, because the two main things we care about are bounds on the steady state means of functions, and this is a value function that we'll be using a lot, and we get bounds on both under this one simple condition. And then plus, well, we need something though. Did I say it? Under that, which will always hold. The fact there's one state which you can reach with positive probability from any initial condition. All right.
And that's only for S finite?
That was before you came in. I said, you know, it's really painful for me to stick to countable state spaces because this is completely generalizable. It's just that I have to tell you what I mean by a small set for a general state space, you know, and it requires. I've tried in the past, and I found it just turns too many people off. So basically, I do have the countable state space, and if you're interested in those notes, so those notes, I don't expect you to read those 33 pages of notes, but just think of it as my gift to you. It's like a summary of my book with Tweedy and the appendix of my networks monograph. And it does give all the details. It explains what a small set is. It actually has a proof that this implies this, even in the case where there is no point, where there's no such thing as tau. There's no point that you reach with positive probability. You know, like a Gaussian model, you know, where there's no single point you hit with positive probability. Yep.
You said that h of x is less than or equal to const.
A constant, yeah.
Times that.
Yeah, times v of x. And I go +1, because I'll make the constant so large that it wipes out.
Some constant h x times v of x plus 1.
And I should put absolute value signs here, yeah. It's a multiplication, it's just a product there. Sorry.
Oh.
I'll put a dot, that's right. Yeah, I just mean, you know, I mean, actually, it's stronger than that, right? I mean, we have, you know, f is positive here, so we can make it 1 for h and something else for the negative side. I don't know. Never mind. We could refine this if we wanted to. All right, there's so many things to say. So, all right. So I didn't get any pushback about where to go with this. Nobody said, no, I want to start doing deep Q learning next week. I mean, I would have said no to that. But I'm just going to go. Joel was the only person who passionately asked for us to stay on script and discuss and develop the theory in the uncontrolled case more before we jump to controlled models. And so I'll do that. And which means that first we've got a result here. It's completely scrambled, but I'm not going to rewrite a theorem on the blackboard. You've got in your notes. Theorem. Suppose that you have a X star irreducible Markov chain, and suppose that this condition V3 holds. Then an invariant probability mass function exists, and its mean is bounded. You can get an explicit bound if you want. In fact, you can even prove that. And you get explicit bounds on the solution to Poisson's equation. So that's like theorem 6.20.2 in those notes. Okay, so you can look that up. One thing to note is that, it's kind of cool that you can get this bound without any conditions on V. V is not negative. But if this was a finite state space, I've already told you it's trivial. I multiply pi by both sides, and I say pi d is 0. All right? And then I get pi of f is less than b times pi of s. But what's cool is you can get that even when the mean of v is infinite. So that trick I did before, just hitting both sides by pi, doesn't work. if you unaccountable state space, you don't know anything about v, so you can't justify that. So all this work is just because of that one subtlety that I don't know that this function has 0 mean if I'm not in a finite state space setting. So I gave you a homework assignment. The very first problem is an example where that's true, where a function, Markov chain, very simple one, a function v, and you hit v by d, and it doesn't have mean 0. So that's why there's subtleties in this area when you get past the finite state space. All right. All right. Yeah. Oh, well, no, X star irreducible just means there's a positive probability of reaching it. A Q, an unstable Q, as long as there's the service rate, like an MM1Q, as long as the probability of going downwards is positive, is X star irreducible for any X star. It's irreducible, right? But that load parameter, if the arrival rate is greater than the service rate, then the process just linearly explodes to infinity, even though it is X star irreducible. Yeah. So X star irreducible is not a stability condition. It's a communications condition. No. I mean, no. It's only positive. No. Let's remind you. I'm glad you asked that. I'm sure that people have the same question. It's that weak. It's only the fact that the probability that I reach X star, that's positive. That's all. So it might be very, very small. Like for a Q, for an unstable Q, this would go to 0 geometrically fast as X goes to infinity. All right. All right, so let's play with this a bit more. So we've got a theorem. A Lyapunov function implies a bound. And let's go backwards. Let's assume a bound and get a Lyapunov function. And this is for people who, more than anything, this is for people who have studied nonlinear control. And there's beautiful if and only if conditions there. It's just as simple here. It's simple if you understand what these stopping times are. Thank you. Yeah, I mean, it was really like all that stuff about the strong Markov property and everything. Really, it was really important to think of this as a function. Expectation itself is a function on x. So when I write e sub x, I mean that I initialize with the value x, and we're about to use it big time. Okay. And I'm doing this for intuition and to practice these concepts, okay? So here it is. I'm just going to give you one example. Like every one of these Lyapunov conditions has a converse theorem, and they're always of the same flavor. So here it is. And I'm gonna put this, sorry. So I've got a bound, the bound that I was able to deduce before, that this cost up until this time I reach x star is you think of f as a cost function just for the fun of it. This total expected cost is finite for every initial condition, and again assume f is greater than or equal to 1. Then this condition v3 holds. And, okay, so I'll remind you, so tau x star was the first return time. We're taking a min over t greater equal to 1. And the sigma was the first hitting time. T greater equal to 0. It seems really crazy to devote a whole symbol to a sigma and a tau. But you'll see in a second there's a really good reason for it. Okay? Because sigma, of course, is 0 if I start at x star. So which makes it a pretty boring stopping time if you start x star. And that's not the case here. That is the first return time. You're looking at t greater equal to 1.
I think you say that sigma equals tau except if you start x star.
Thank you. Yeah. And I didn't like this when I first saw it, but I learned to like it. You'll see, you'll see. It's useful, you'll see. All right, so the proof of this is really easy once you understand these shift operators and how to play with them. All right, so remember what is dv3? I mean, v3. That PVF is a conditional expectation and involves the shift operator and all of that. And we'll have to explain that. Let's do this slowly. So what is PVF? First, I'll just remind you, we're summing over y, or x prime if you like. I'm just to remind you, we haven't left the universe, but that's not a useful representation at all. Not at all. It's useful to write a conditional expectation. It's all right, which I've also written, it's much easier to write that. Gulp. Now, that means I have to take this expectation, and where the x is, I have to put in a random variable, which is supposed to make you feel nauseous. But let's do it, and let's see if you remember last lecture. I'm just going to write it like this. All these symbols are too confusing. I've got a random variable h, okay? All these bloody symbols will just confuse you. What is that based on last lecture? Remember the Markov property and the strong Markov property? Where does the shift operator come up? So the expectation sub x1 was a conditional expectation, but I had to monkey around with h. This has a representation from last lecture. I'm just slowing myself down in part. Because this looks really strange to take an expectation and plug an x at 1 and all that. But it's not, because this was the subject of study last lecture, the first half. The shift operator, conditional expectations. Yeah, I heard enough. Now this is the most primitive use of the shift operator, but it sure does make your brain more fluid. Being able to just do that without thinking is so nice. So this was the Markov property. I could, instead of 1, if I had a stopping time, I would have had, instead of 1, I'd have a tau there and a tau there, And so that is a thing we have to now, take apart and think about, what does it mean to take that random variable and hit it by the shift operator. So we have to figure out what is theta to the 1h equal. And, you know, let's just go play with this. So let's do it. So it's having a random ending point is annoying, get rid of it. That's the first thing. So whenever you see these random sums, make them a deterministic sum, but then pin here. So I'm only summing over t's that are less than or equal to sigma. All right? But now when I hit h, you know, when I do this, it's a completely linear operation in a sense, because all I'm doing is I'm taking the sequence of omegas and shifting them by 1. And we know when you hit this by the shift operator, you just replace t by t plus 1. You know, we saw that last time. You know, this whole thing is a function of this thing here is a ft measurable random variable, meaning it's some function. I don't know what function it is. We could write it down. We could write it down. Let's not. It's some function of the first t observations. That's because sigma is a stopping time. You know, this is actually, well, it's actually ft minus 1 measurable, but it's ft measurable. You know, that's a part of the definition of stopping time. Okay, so this can be written like this. When I hit this by theta, if I hit this by theta, I just shift those indices. All right, so this whole mess is just, I can just go through and do it. It's f of x of t plus 1, indicate a function that theta 1 sigma is greater or equal to t. You know, here I shift the dependency by 1. That's some, you know, that's part of ft. I mean, really, fuck it, let's just do it. You guys help me. When I wrote this down, what did I mean? All right, it depended on the last term by f. And what does it mean to say sigma is greater or equal to t? It means that sigma is greater than t minus 1. Why am I being coy? Is that obvious, right? The indicator function sigma is greater or equal to t is the indicator function sigma is strictly greater than t minus 1. Because I'm not saying anything about time t. It could be there, could not be. That just means that I wasn't there for the previous t time steps. All right. So when I shift this, I add 1 to there, and I add 1 to all of those guys. All right. Yeah. Yep, I'm not waiting.
So what you're saying is that basically, if the indicator is on at time t, it was on for all previous t.
Well, that's true. But that was true up here. right? I mean, here this is 1 up until t is bigger than sigma, and then you turn it off.
Right.
But I'm just trying to say, it looks really weird to take this shift operator and plug it inside. It looks really strange that it commutes with anything. And it's just the fact that it commutes with anything, because by definition, all you're doing is shifting the arguments, you know? You have a string x0 to xt, replaced with a string x1 to xt plus 1. And so it's a magic operator that commutes with anything. That's what it really looks odd. And, yeah. Yeah.
If that's the case, is this true in the scenario where you have, or I don't see how it could be true in the scenario where you have the first return time? Don't you then have x is 0 is equal to x star?
No, this is just this is just a definition of a shift operator. If I have a function, a random variable this form, I hit it by shift. By definition, I just add 1 to each term. That's just the definition of the shift operator. So there's nothing, so far there's nothing special about how sigma is defined. You know, this is a property of, this was a property of stopping times. The fact that that is a ft measurable random variable means it's a function of the, it's not of this form. I mean, if sigma was not a first hitting time, it wouldn't be of this form. I wouldn't be able to explicitly write it down. For any stopping time, I'd get something like this. But this is all I need. All right. And actually, let's keep that. I was going to, let's do this again. So I'm just writing down what I said before. So I could, like I said, I can move these all over the place, take them in and out, all I want. So if I take, in fact, I'll just take that out in, it doesn't make any difference. If I take this random variable and I shift it through this operator, I just add 1 to each guy. And does that look familiar to you? So I've got conditions on, I've got conditions on times 1, 2, 3, and so forth, not 0. And that's what tau was defined to be. This is exactly equal to the indicator function that tau is strictly greater than t. So I had a indicator function sigma greater equal to t. Now I've got a indicator function tau strictly greater than t. You know? But as was astutely pointed out by you or somebody else, tau and sigma are the same unless you start at the special state. So there we get it. Okay, and these were, our initial condition didn't change. We're starting at state x. So this guy here is exactly oops. So first of all, I shifted f, and this became tau greater or equal to t plus 1. Right, because saying that tau is greater than t is the same as tau is greater or equal to t plus 1. And think about this. Check it out. I mean, this looks exactly like the sum from 0 to tau, but we lost the first term. Yay! We did it, right? So I've got PVF equals something minus F. That's just what I wanted almost. But what do I have to say now? I have to use the lemma that somebody shouted out earlier, the fact that tau and sigma are the same if x is not equal to x star. And I've lost v of f of x, didn't I? I can write this down with confidence except for when x equals x star. But if x equals x star, you go check the definitions. These guys are the same. So vf of x equals f of x if x equals x star. And so then I could just put in an indicator function. And B is that. This is just a way of doing an if statement. You know, if x is not equal to x star, we just prove this. You know. And if x equals x star, this is 0, and we just get this, which is just rewriting, well, actually, well, put in a 1. Check it out, I mean, because there is a term missing, actually. What's that?
That's something you just said. The one inside the expectation.
Oh, say it again? You know what? No, this was right. No, this was from what, you're absolutely right. Here, I'm always, the argument here is always greater or equal to 1, right? So what I did here is I cheated. I stuck in a t equals 0, and I subtracted it away. So I did that, that was a card trick. I did it too quickly. All right. So this was a sum from 1 to tau. And I just maybe I did that too quickly, but I put in the 0th term and I subtracted it away. Yeah. Is that clear? Anyway, but you all think of the same way that I was able to decompose the sum with sigma. I have exactly the same decomposition here, but I'm missing the first term, which is what you're pointing out. And that's why I'm subtracting this off, because the first term is missing.
Why is it equal to 1?
Oh, because take a look, exactly what I'm saying right now. You see, this is a sum from 1 to tau, not 0 to tau.
If x equal to x star, then we get
Yeah. We get from 0 to tau, that's right. But I've got the minus f, and that cancels out the first term. It makes it simpler. No, it doesn't, because when x equals x star, this is f and this is f, so these cancel out. Yeah, it really does work out nicely. And it gives you what you want, too, because after all, remember, the mean of f is nothing but, I mean, it's consistent with what we've seen before. Well,
So this result holds
anyway.
even if x is equal to x star.
That's what I'm saying. So, whoa. No, this statement here is just saying tau and sigma equals x star. And that's how I was able to first convince you all of this when x was not equal to x star. Absolutely. In the special case x equals x star, we have to think differently. We have to go back to this calculation and just notice that this whole thing is just nothing but that. Yeah. All right. Okay, cool. So now shall we do Molly-Von calculus and in the spirit of last lecture? No, I think that's as much. So there is like half of those 33 pages are on things like this, on bounds on Lyapunov functions, converse theorems, all sorts of things, and way more than we can cover this course, okay? And I'm going to cover less this semester than in previous years because I want to cover more on stochastic approximation. So that's it for Lyapunov theory, pretty much. We have a one direction. If a Lyapunov condition holds, we get bounds. And conversely, if we have bounds, we have this beautiful condition. This, poetry, if you ask me. But that's it. No more poetry on that. I'm going to follow Joel's plan. Next lecture, I think in 2 hours, we'll do coupling and the ergodic theorem. And then that'll set us up for value iteration for computation, which also uses coupling ideas to understand convergence and all of that. And then that'll be it. We'll leave uncontrolled Markov chains. I think by a week from today, we'll actually look at the control. It's my feeling at the moment. Yeah, unless I'm going way too fast. I don't know. All right, because there's no way I can say anything more. That's yeah. But Claire?
A good amount of homework.
What?
Doing